Today we will see some of the applications of shift registers. We talked about flip flops, counters and registers. Registers are group of flip flops in which you can store data. Then we said the shifters, the registers can have a shifting feature, so that once you put a data, you can shift that data either to the left or the right, and these are called shift registers. There are lots of applications. Of course, we saw applications of flip flops and counters. Likewise, there are applications for registers. The most prominent application of registers is the memory storage. Use them as storage elements. Shift registers are sometimes used for other applications. I thought we will see some of those applications today. Shift register applications. So, let us for example take a 4-bit shift register. With a shift right feature. So, it is a 4-bit shift right shift register. So, this will have, let us assume this is a serial in, parallel out. That means you can put the data, also you can, serial in, parallel out does not mean you cannot put parallel data. Parallel input also will be there with the loading feature, but otherwise normally data is put through the serial. So, this will have the data in a clock, of course, clock, either positive edge or negative edge, does not matter. The input of the serial input is called serial I, serial input, and the clock will shift the bits. We should also have load and clear features, because you want to start with a pattern. That also you can do by putting the data one at a time and shifting it. That is one way of loading. The other way of loading is to give parallel inputs and then give all the bits at the same time. So, outputs, so these are parallel outputs, these are Q, call this A, B, C, D. These A, B, C, D again. First you put a pattern in this, load it. Of course, you want to clear it later on, you can do a clearing. Then you clock it. As you clock it, the bits get shifted 1 position to the right. That is why it is called shift register to the right. So, what I am going to do is to take the output of these and output of this, into an exclusive OR gate and feed it as the input. So, every time I clock it, this bit goes here, this bit goes here, this bit goes here, and the exclusive OR of these 2 bits is loaded as a fresh input. So, you can, as you clock it, this will go on. So, let us assume that it has an initially I am able to load a pattern of 1 0 0 0, initial pattern. Just assume that, you can assume anything, I am just assuming this. So, I am to start with a load 1 0 0 0, Then with the next clock pulse, at first clock pulse, what will happen is this 1 gets here, this 0 gets here, this 0 gets here. And a new bit will be added to the input, which will go into QA. Since this is an exclusive OR of C and D, what will be the exclusive OR of C and D? 0. So that 0 will get into this position. So again I shift it after the second clock pulse. This will become 0, 1, 0. This is also 0. After third clock pulse, 1. Fourth clock pulse, 5th clock pulse. What will be this? What will be the new bit? 0. One, exclusive OR these two. All you have to do is to shift these 3 bits here and get the exclusive OR of this here. Right. Now after this, this will be 1, 0, 1. What? 0, 0, 1, 0, 1. 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, this will be 1, 1, 1, 1, 1, then it will be 1, 1, 1, 0. I will write here. After this, it will be 0, 1, 1, 1, 0. Then 0, 0, 1, 0, 1, 0, 0, which is this. So, by just putting one initial pattern, of course this is only arbitrary pattern, it does not have to be 1, 0, 0, 0. You can put any other pattern too. And I get shifting every time you apply clock pulse, the bits get shifted 1 bit position to the right, and a new bit is added to the right, new bit added to the left, and then again shifted and so forth. So what happens is how many different patterns are here? This is the starting pattern. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 patterns. Again it repeats. So after the first clock, second clock, third clock, fourth, fifth, sixth, seventh, eighth, 10th, 11th, 12th, 13th clock, 15th clock. So this is 0. So 15 clock pulses. After 15, so the frequency of repetition is 15 clock pulses, duration, 15 clock durations. During 15 clock, after 15 clock pulse, the original pattern is restored. Okay. Now there are only 16 possibilities with 4 bits. So I get all except one. I don't get 0, 0, 0, 0. If I get 0, 0, 0, what will happen? It will keep repeating. So I should not put a 0, 0, 0, 0 to start with, because when you put 0, 0, 0, 0, it gets shifted to 0, 0, 0, 0. Again it gets shifted to 0, 0. So if you leave 0, 0, 0 out, so you load anything other than 0, 0, 0, 0, I get all the other 15 patterns and then it gets repeated. Such a circuit is called a pseudo random noise generator. Not necessarily noise, it can be pattern. You can call it pseudo random generator. or if you do not want to call it noise, you can also say pseudo random generator. What I mean is, suppose you want to have a pattern verification pattern, you put a bit pattern which is accepted, and for that bit pattern you know the sequence it has to come. So, you can know whether there is any error in the transmission by, if you agree on the initial pattern, both the sending and the receiving end, for this given pattern you know the sequence of these patterns. I think you can call it sequence generator. I think it is called Peter, I am sorry, it is called pseudo random sequence generator, not it can also be used for generation of noise if you want it this way. But so the advantage of this is I can check the transmission over a period of time. So, I agree on the initial pattern, both sides, receiver and sender, and then start sending data, and as I receive data I check with this, and if there is a change, that means there is something happening to the transmission. Why is it called random? Because the pattern can be also kept secret, in the sense the sequence will depend on the, even though all the 15 patterns will come, all the 15 words, all the 15 different patterns will arise, the sequence in which they arise they will come depends on the initial pattern. If the initial pattern is different, then we will have a different sequence, again 15. So, it is not completely random, you know that 15, after 15 it will be repeated. So, that way it is pseudo random. Pseudo random means semi random, it is not completely random. You know there are 15 patterns going to come, and if you know the initial pattern you can guess the other patterns. So, that is why it is called pseudo random. But if you have this pattern that is given as a test pattern, I can use it for testing. I can give the initial pattern and send it, and then test whether I am receiving the other things in the same order sequence. So, one of the important applications of a shift register, pseudo random sequence generator. And I can now have different values, as I said, the starting value, so that the sequence will be repeated, but not in the same, the patterns will be repeated, not in the same sequence. Or I can tap, instead of here I can do here, I can do here, I can take this and this, and exclusive of 3 inputs I can do all sorts of variations, I can get different sequences and different patterns. So, I can have a simple test designed, one is for our testing the system, the other is for establishing the reliability of the communication between 2 points. If the initial test gets through the other side properly, then we know that the channel is well established, so we can start sending the transmission. This is one of the major applications of, one of the important applications of shift register. We will talk of another application of shift register, which is, let us say again I am going to shift register, and I am just, for the purpose of explanation, I am going to put them as 3 different flip flops. That means I have to, these are D flip flops, or you can even have JK flip flops. I will have JK flip flops. So, I will call these flip flops ABC. They are clocked together. I will not show the clock separately because they are the same thing. I am just showing this drawing, or okay, I can show it separately also, does not matter. What you can have negative edge trigger. Clock. What I am going to do is to connect this J to this Q bar and K so you have 3 JK flip flops, output of first JK goes to second JK, output of second JK goes to third JK, and the output of the third JK goes into the input of the first JK with a twist Q and Q bars. Now I can have this is a shift register in the sense the output of this gets shifted into the every clock pulse, this output goes into this output goes into this, that is why it is a shift register. Now let us say initially now after the first pulse because C which is zeros, C bar which is 1 is connected to J, J becomes 1 and K becomes 0 after the first clock pulse, right. I put 0 0 0, I shift it, one clock pulse shifts this 0 into this 0 into this 0 not back into this, but this 0 is connected here in this one. So after the thing, then the next time will be the pattern will be 1 0 0. After second clock pulse, it will be 1 1 0. Third clock pulse it will be 1 1 1. At the fourth clock pulse it will be 0 1 1. Fifth clock pulse it will be 0 0 1. After sixth clock pulse it is 0 0 0, which is the same as the original. So in 6 cycles of clock I get the pattern 0 0 0 1 0 0 1 1 0 1 1 1 0 1 1 0 0 1. Now if you draw the waveforms for this, how is it going to look like? I will draw the waveforms here. Clock, 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 this is 0 the clock pulse, first clock pulse, second clock pulse, third clock pulse, clock, time axis. Now if you look at this, you can see that after the first initially it will be 0 0 0, then A becomes high for 3 clock pulses and low for 3 clock pulses, high for 3 clock pulses, low for 3 clock pulses, it repeats. Similarly for B remains 0 first 2 clock pulses, then 3, and then next 3 clock pulses 0, next 3 clock pulses 1 and so forth, it repeats. C becomes 0 to start with, for first 3 clocks it remains 0, second 3 clock pulses 1, then again 0, then again 1. So when to draw this for A, B, C pattern, A would be 0, then becomes 1, remains 1 for 3 clock pulses, and then remains 0 for the rest of it. This is the output A. all are time axis. I will not show timing separately. This is the time axis. Okay. B would be first 2 clock pulses will remain 0, the next 3 clock pulses it will be 1, C would be 0 for first 3 clock pulses and 1 for the next 3 clock pulses. So, I have the, I am dividing this clock by what frequency, what is the factor by which this clock gets divided, what is the frequency of this compared to this, time period of this is 3 times less, no. So, no 6 times less. There are this period, for example this period is equal to 6 periods of this clock. The period of this clock is 1/6, or I can put 8, 4 flip flops will become 8. So, the period of this clock is n times the period of the original clock, where n is the number of, n is twice the number of flip flops. So, I should say 2n. The period of this clock is 2n times the period of the original clock, where n is the number of flip flops that are used for this. That is one thing which you can always get by division, but more importantly, if you want to use this as separate clocks, different phases, there is always a phase difference of this much, 1/3 of a clock period, 1/3 of a clock period between this and this, this and this, between this and this. I can get a clock period, it is called multi-phase clock, multiple phase. So, I have the clock period, is 6 times, 2n times the system clock period, we will call this system clock, and there is a phase difference between, there is a phase difference between 2 successive waveforms of phase difference of 1 clock period between successive clocks, 1 original clock period. Sometimes it is useful. So, I want to have some lights going in a sequence. Supposing I turn on lights and turn off lights using this. This light will be on at this point and it will stay on for 3 clock periods and then it will become off. This light will be turned on after a delay from this light, again it will stay. So, before that it will go. So, first this will light up, then this will light up, then this will light up, and this will go, and this will go, this will go, right. So, some sort of application like that where you need multiple phases, it is called multi-phase clocks. Multi-phase clocks when you want for some system use. Use it. Such a, this is also called a counter. See, counter is basically what to do in a counter. Counter, you give a clock pulse, divide that clock by a factor of 2 by every flip flop, frequency is divided by 2 in every flip flop stage. So, same similar thing here, similar thing here. So, this also counter, but only thing the output of this counter we twist and then connect it. So, a counter which output of 1 is go to the next, output of one, second go to the third, output of third goes to fourth, output of fourth goes back to the 1. Without twisting it, if I do, you can take it as an assignment exercise. You connect q back to j and q bar j back to k. Of course, if you put a 0 0 0, nothing will happen. Anything other than 0 0 0, you put and see how it. So, it is a shift register basically, that is all. 1 0 0, 0 1 0, then 0 0 1 1 0 0. So, it will only repeat shift register. That is called ring counter, a counter wherein we use the output of the last flip flop back to the input of the first flip flop is called a ring counter or recirculating shift register they call it. You circulate again and again the same pattern, but this counter is slightly different from the ring counter. It is called the twisted pair ring counter. So, we have let us say recirculating shift registers, ring counter. Recirculating shift register is same as the ring counter in the sense I have this flip flops, serial output is fed as serial in. Put a pattern and keep circulating it. That is what will happen in a ring counter. Put a pattern and connect it back. You can use a D flip flop for that matter. You do not need to use JK. If you want, you can use JK too. But this shift register, which uses twisting of the output back into the input, is called twisted ring counter. What we have seen it as twisted ring counter used for multiple phase twisted ring counter. For using this multiple phase clock generation, and the period of the clock will be 1/6 of the period of the original clock with a phase difference of 1 clock period between 2 phases. This counter is also called a Johnson's counter. Johnson counter. Again, it is used commonly for multiple phase generation. As I said, you want to have lights turning on and turning off in a particular sequence, you can do this. That is one example. Now, if I do not want this phase to be of this duration, 1 period of clock, I want only 1 clock period with different phases. That is, I want a clock to be on, I want one pulse to be on for this period, 1 period, another phase, another clock to be on for this period. We have 6 periods, right. Suppose I want pulses like this. All the T. What I am saying is, instead of this light, say take the same light example. This light is on at this point in time and remains on for 3 clock periods and then switches off. This light is on in the next clock period, after the next clock period, but it remains on for 3 more clock periods and so forth. I have 3 lights. Turn on, this turns on, this turns on, and I can have them on for half the clock period and other half the clock period will start disappearing. 1 and then like this. Instead I want a clock 6 phases, but only each duration should be, I should have 6 LEDs or 6 lights which should be turned on each only for one clock period, original clock period. That means I want something to be on for this period alone and off for the rest of the period. It can be a motor, it can be a light, it can be something which you want to just activate for this clock period, another only for this clock period, another only for this clock period, this. So, from these waveforms I should be able to generate these waveforms easily, because if you look at this ABC, you can also write, I can write ABC here. We started with 0 0 0, then we made it 1 0 0, 1 1 0, 1 1 1, 0 1 1, 0 0 1, is it not? Back to 0. Suppose I take the complements also at the same time. So, each of these flip flops have Q and Q bars. So, I can call this A B C, this is A bar, B bar, C bar. So, similar to the A B C, I can draw waveforms for A bar, B bar, C bar, which will again have the same on period for 3 clock pulses, off period for 3 clock pulses, but that will be complementary to the corresponding clock. A bar will be complementary to A, say inverse of A, B bar will be inverse of B, C bar will be inverse of C, again on for 3 clock period, off for 3 clock period, total clock period being 6 times the original clock period. Now, I can see the pattern such that I want something to be on only for 1 clock period. Now, there is a, you can look at this, for example, if you take B bar and C bar are one only for the first clock period. Let us call this first clock period, second, third, 4, 5, 6. Suppose I say A bar, B bar, C bar. B bar, C bar is one only for this clock period. Is it not? Huh? Okay, it's wrong. I am sorry. Second one also it is wrong on. We can make it A bar, B bar, A B bar, first clock period will be on A bar, C bar, not B bar, C bar. So, A bar, C bar is on only for these 2 clock period. For this clock period, A C bar only for this clock period, right? A C bar only for this clock period is on high. Just A C bar, no, that is wrong. A bar, B bar, C bar. A B bar, A B bar, right? Is A B bar on only for this? A B bar, correct. A B bar, A C bar, is all right? Second is all right. What is third one? B C bar, B C bar, right? B C bar. Fourth one will be AB can have this, no, AB, AC will be there, AC will be on only for this. This one would be A bar B, A bar C would be A bar C, this A bar B, yes. I think the complement of this. This will be B bar C bar, most probably B bar C, B bar C, complement operations. So, what I have to do is, all I have to do is to get the complement of these waveforms A, B, C, A bar, B bar, C bar, and then use AND gates. So, in that case I will have, so this is what the first clock period is on A bar, C bar. Of course, I am not showing C bar, I am not showing A bar, B bar, C bar. You can imagine that it will be the opposite of this. This will be A bar, this will be B bar, this will be C bar. So, you can imagine these waveforms can be clubbed from A bar, C bar here, A B bar, A B bar, B C bar, A C, A bar B, B bar C. So, I have now variety of choices now. I can either have 3-phase clock with the same period of 6 times the original clock period. So, I can have a light on overlapping, 3 lights on, first light will be on, second light will be on after some time, third light will be on after some time, and then the first light will be off, second light will be off, third light will be off. That type of display, if you want, you can have it. Or I want to have only a light on for this period, first light, and then it will go on, then second light will be on, that it should go on, third light should be on. They have 6 lights which should be on for 1 clock period each of the original clock, and then again it will repeat. So, all these applications are possible by Johnson's counter or twisted ring counter, which is a basic modification of the shift register, as I said, because shift register basically is the output of one stage fetched into second stage and shifted to the left or the right, depending on the other 2 applications we saw the other day were the parallel to serial converter. Supposing the serial data is coming, I gave you examples of data coming through telephone lines in bit form, and you want to assemble it as words, serial to parallel conversion. Or you have the computer generated data which is available as parallel data, bytes or words, and you want to transmit it through your telephone line, you have to shift it serially and send it. So, other applications are then parallel to serial converter and serial to parallel converter. So, shift register is a very important what shall I say, the building block of a sequential system, of any digital system. These are all building blocks of digital circuits. First we saw combinational building blocks, gates, adders and all that. We saw then sequential building blocks, flip flops. Using flip flops we saw how to build counters and how to build registers, how to build shift registers, and shift register is a very frequently used component in many digital systems. I have given you some application today, the pseudo random sequence generator, the Johnson's counter, and then the parallel to serial, serial to parallel we talked about the other day and all that. So, with this we are more or less completing the discussion of the basic building blocks. We have to talk of some other building blocks in combinational domain, multiplexers and all that. But what I want to do now is to talk of now systems. We will use multiplexers, decoders and other combinational building blocks which are not basic building blocks like gates gates are the basic building block in combinational, flip flops are the basic building block sequential, but I took a flip flop application and developed into counters and registers and shift registers. Like we did in the case of gates, we took the basic building block of gates and developed them into adders, subtractors and all that. So, now there is a whole lot of things can be added. These are basically built using the basic building blocks. Combinational basic building blocks are gates, sequential building blocks are basic building blocks are flip flops. Now, we can use all these things to build subsystems or second order type of complexity, and then using them we have to build systems. So, we have to get into the act of how to define a system, how to synthesize it, how to build it. Before that, we will just to deviate for a minute and say here now, why did I now start from gates and finish gates, and then instead of doing the other things like multiplexers and decoders and other programmable arrays which are all combinational building blocks, switched to sequential in order to give you all the basic building blocks in both combinational and sequential, basic tiles like a Lego block I told you. Basic tiles are there, it is up to you to play with them and then build castles. Now, why did I do that is because technologically these are of the same complexity. We have generally we define systems as small scale ICs, all these are integrated circuits. It is made of silicon, but then built as a one single circuit. A gate, even a gate is an integrated circuit in the sense gate is not a component, it is the basic component of a gate is a transistor, maybe a field effect transistor, MOSFET as they call it, metal oxide semiconductor field effect transistor or bipolar junction transistors. Sometimes may use extra components like resistors, occasionally capacitors. So, using all these things you build a basic building block which is an integrated circuit, because all these things are integrated. The circuit is integrated in a small single piece of silicon crystal into which you etch this by lots of means. Etching is a very crude term today. Etching is usually earlier on it was done by chemical process. Today we have so much precision required, all these things. We have lithography using lasers, using electron beam, molecular beam and all that lithography, so that you can precisely cut. Like even in surgery, you know, now today, earlier on people were used to be operated, they have to cut open and do all those things and then close it. Today everything is done by precision beams, laser beams being sent. And so likewise in a building block also we have transistors and gates and things like that. Because the technology has grown very, very precisely, they are put together in different places and formed into a single circuit. These are called integrated circuits. Now, general integrated circuits are any circuit in which several components, both active and passive. Active components are transistors, diodes, FETs, etc., and passive components are resistors, capacitors, inductors. Of course, it is very difficult, it is relatively active devices are easy to make, passive devices are little more difficult, resistance is okay, capacitor a little more difficult both in terms of size and the precision values, and inductance is even more difficult, but we will see all those things later on how they build all these things. But these integrated components, integrated circuits are classified into small scale integrated circuits, medium scale integrated circuits, large scale integrated circuits, very large scale integrated circuits. A small scale integrated circuit is a circuit in which about 10 gates in one circuit. Some simple a gate is an equivalent function. Do not think that gate has to be a gate, in sense I told you a gate will have a few transistors and a couple of resistors. So, if you think of that as a basic building block, 5 transistors, about 2 resistors, something like that order, as one unit of gate we will call it gate function. It is not a gate as per se, it is a gate function. Up to 10 gate functions in a single circuit is called integrated circuit. So, this is not approximately. Any circuit which can do an equivalent function of 10 gates, up to 10 gates, AND gates, OR gates. Supposing you draw a simple combination logic circuit with some few gates here and there, equivalent of that 10 gates, we call them up to that small scale integrators. And then from 10 to 100 approximate, these are approximate thumb rules, nobody defines this, it is not numbers like Planck's constant or something which cannot change or anything. It is not approximate, just to give you the idea of the complexity. Somebody gives a circuit, say how many gates, you give me a circuit, I will say how many gates, you say 1000 gates, does not mean 1000 gates you put. This circuit will do things which is capable of being done by about 1000 gates, that is what we mean. Up from 100 to 1000 it is called LSI, and beyond 1000 it is called VLSI, but of course today people sort of ULSI and all that, I do not believe in all that, ultra large scale integrated circuit, but then anything which big, there is no between VLSI and ULSI and all that. Somebody says beyond 100,000 it is ULSI and all that, it is all individuals' opinion. So, this is basically a structure, and why I finished all these basic building blocks and combination and sequential is whatever you have done is up to now is can be generally classified as small scale circuits. When you put more of these gates, the functional complexity increases, they become medium scale integrated circuits, and then you more and more of them become large scale integrated circuits. So, basic level we have now understood the basic building blocks, bricks, and we will use those bricks to build a system, subsystems which are medium scale like multiplexers and other things, and in the case of 4-bit full adder may be qualified to be a MSI. Similarly, 8-bit shift register, 4-bit shift register, 8-bit shift register may qualify to become MSI. So, then we will do MSI functions and then how to use them directly in our, instead of going to gate every time, because if you are giving a very large circuit like a microprocessor asks to define, you cannot go to the gate level and design, because a microprocessor may have 300,000 gates, 100,000 gates like that. So, I can give you a circuit diagram with 100,000 gates connected, mind boggling. So, I have to think of higher levels of abstraction, it is called level of abstraction. Higher level of abstraction, I will talk about MSI being directly used, LSI being directly used to get VLSI and all that. So, we will see from next lecture, starting next lecture, we will see how to build using these basic building blocks of both combinational sequential, how to build systems which are meaningful in the sense of system design. They are basically smaller system to start with, and later on probably we will do 1 or 2 bigger systems. Just to get you some ideas, we will start with the small circuits.